Good morning, Astronomy 1020. Welcome back. Today, we'll do the second part of Lecture 4. You're going to learn about energy. You're going to learn about temperature versus heat. You're going to learn about atoms and molecules. And then we'll even start to talk about light, which is going to be an expansive subject in this class. So let's start off where we left last time. Hello. Oh, hey, Noel. How are you? So nice to see you. Now, here's an old friendly face that I like to see. Welcome back to our lectures. Anyways, you guys learned a little bit about gravitational potential energy last time. So tell me what you learned. What the hell is gravitational potential energy? Did anyone learn anything from my lectures, or have I failed you as an instructor?
It's energy stored in the gravitational field.
That's correct. You're storing energy somehow in a gravitational force field. And how does the formula look?
It's mass times m times g times h.
Excellent. Mass General Hospital, right? MGH. And the setup, of course, you'll remember, is you just take something that has mass, like this ye old 1 kilogram test mass, and you just simply lift it against the will of gravity. You pull it up into the air, and you suspend it some height above the ground. M is the mass, H is the height that you've lifted it up, and G, of course, is the local acceleration of Earth's gravity, 10 meters per second squared, which is roughly the same value as long as you stay on planet Earth. One can also define potential energy in other places in the universe, and it follows a similar formula, but we have to expand upon what we mean by G. We have to account for the fact that different planets, different types of things like asteroids and moons have different G forces associated with them. But if we start off by sticking to Earth, we're storing energy by holding this mass suspended in the air against the will of gravity. And at any point, we could choose to drop it and let it go and release that energy back to the Earth. Last time, I took a test mass of 1 kilogram. I suspended it at a height of 2 meters. And what did we discover our potential energy was? This is the very last thing we did before class ended. Okay, well, then you're going to have to do it again. See, if you can't remember things, then you have to do the same thing you did before. You have to multiply the mass, 1 kilogram, times little g, 10 meters per second squared, times a height of 2 meters. What is 1 times 10 times 2? Arunsak, tell us what it is.
It's 20 joules.
20 joules. And how do we define the joule, Arunsak? What is a joule?
It was kilograms m squared over s squared.
The joule is the standard MKS unit of energy. Why don't we do let's do a little riff on MKS versus other units of energy, okay? Before we go any farther, I'm going to erase here. And we're just going to talk about units of energy. In the MKS system of units, our standard unit is the joule, which is defined as 1 kilogram times a meter squared divided by a second squared. That's our standard unit of energy. a kilogram meter squared per second squared. There are other units of energy. I don't suppose anyone knows. What do we use in the imperial unit system, which is what America uses? Hold on, I'm hiding the trolls here. I don't want to see any more trolls. Okay. Watts, Devin, are unfortunately, pounds, Arunsak, are an imperial unit of force. Watts, Devin, are an MKS unit of power, which is not the same thing. Have you ever heard of calories before? The calorie is a unit of energy. We can talk about this. In the imperial system of units, 1 calorie with a lowercase c is equivalent to 4.2 joules. Therefore, a calorie is actually similar in scale, in scope, to a joule. However, that's not exactly the same as the food calories that you find on packaging. And the USDA, I guess, whoever defines what calories should be labeled as in a package, let's just call them food calories. A food calorie is actually, and sometimes we use a capital C for a food calorie, is actually 1 kilocalorie. Sorry, I gotta use a lowercase now. We have to be consistent about this. Is actually a kilocalorie, or 4,200 joules. For some reason, the USDA or whoever decides what food packaging should be labeled as, or maybe it's the FDA, I don't know who does it. In any case, some governmental powers that be decided that we couldn't use kilocalories on our food packaging because then we might sound like our snobby European friends. And, you know, metric units just really confusing. They're not intuitive at all. So they decided to rename the kilocalorie as the calorie, capital C, leading to hideous confusion when you're trying to talk about calories, whether you mean the imperial unit or whether you mean the sort of food calorie unit. How about when you pay your electric bill? Anyone ever pay their electric bill? What units do you pay for when you pay your electric bill and your gas bill? Sorry, Stacy, you're muted. Caroline, do you want to try, Stacy?
Sorry, I was going to say kilowatts.
It's not exactly kilowatts. It's going to turn out that kilowatts, like watts, are a related unit of power, but they're not the same thing. If you look carefully at the billing subscription, you will discover that you're actually paying for kilowatt hours. That may come up in our homeworks today. It's a kilowatt times an hour. A kilowatt hour. Yes, Stacy, you have a very nice backyard. We all wish we were there, hanging out in the sunshine. What about gas bill? Have you ever looked at the gas bill? I believe they call them therms on your gas bill. And therms are short for British thermal units. If you ever go buy an air conditioner during the summertime, they will rate the cooling power of your air conditioning in BTUs, or British thermal units. And they also, you know, they do the same thing for space heaters. I believe that I'm not 100% sure, but I believe that the therms on your gas bill is code for British thermal units. Today, I'm going to be teaching you about another unit of energy, a really tiny microscopic unit of energy that's used when we discuss the world of atoms and small particles of light and things. And that's called the electron volt. The electron volt is abbreviated 1 lowercase e capital V, and is a tiny little packet of energy equivalent to 1.6 times 10 to the minus 19 joules. That's an important conversion factor that you'll want to have in your back pocket at some point during our lecture today. So you can see there are many different possible units that you can use to measure energy. You guys are perhaps most familiar with food calories, but going forward, the joule will be our standard unit. Let's say we wanted to have a snack, right? Like, here's a Cascadian Farms granola bar. Yummy, yum. Protein. I might actually eat this thing during our lecture here today. Let's look at our quote unquote nutrition facts. And it looks like this thing is rocking about 240 calories. And I'm kind of hungry, so I'm thinking about eating this thing, okay? So I'm about to ingest 240 calories worth of Cascadian Farms peanut butter and chocolate. Okay? Now, once I eat this, I'm going to start to feel bad because maybe I haven't done enough exercise this summer. And I'm going to start to think about my sins and how I could atone for them. And I'm going to want to do some exercise to burn off these 240 calories. Is it vegan? Hell no, I hope not. Otherwise, I'm spitting it out. Although it doesn't look like there's any fish in here or any other food product or animal products. Who cares? It's tasty, all right? Anyways, once you eat it, you're going to start to feel bad. And then you're going to want to do some exercise. But we need an exercise regimen appropriate for a wimpy physicist such as myself. And I'd like to introduce to you my new exercise routine. It's going to be called the 1 kilogram squat, okay? What I'm going to do is I'm going to put this thing down on the ground, all right? And I'm going to bend over and go, and I'm going to pick it up and I'm going to lift it 2 meters above my head. And that's going to be my exercise, 1 kilogram squat. And what we would like to know, well, first of all, let's take a look at this here. Hopefully you have that all written down. So suppose a candy bar has a total energy content of 240 capital calories, okay? And I want to do some exercise to burn it off. And my exercise regimen will be called the 1 kilogram squat, okay? How many joules do I have to expend to do a 1 kilogram squat, students? Jesus Christ. It's like pouring water through a colander. Okay. How much energy does it cost to lift a 1 kilogram mass 2 meters above the ground?
20 joules.
Thank you. The 1 kilogram squat putatively will burn off 20 joules. The question that we want to know, the question that we'd like to answer is, how many squats do I need to burn off the 240 calories? Austin says 50,000. I don't know if I believe you, son. I don't know if I believe you. Austin, where are you? Are you a troll?
I'm a troll today.
Oh, gosh. Or Wyatt, I'm picking on you then. Wyatt, it's nice to finally see you out of Trollville. Wyatt, could you help me figure out how to solve this problem?
I mean, I can try.
What's a technique that will help you solve this problem flawlessly? A technique that I trained you on. There's a way to do this. There's a good way. Does anyone know what I'm talking about? Probably not, huh?
Conversion?
What? What's that?
Conversions?
Convert.
Like the conversion formula?
Dimensional analysis.
Analysis.
Okay.
That's what I want.
Okay, so get out your 4 steps of dimensional analysis, Wyatt.
All right, so you gotta have the first, whatever you're trying to convert.
All right, so what's that?
Are we converting the calories?
Well, see, that's an interesting thing is how do you start? What are we trying to convert?
Yeah.
What do you think?
Well, okay, so we're trying to figure out how many squats we need to burn. Okay, so we need to figure out how many how many joules is going to burn how many calories, right?
Kind of, yeah. But let's start with the number we're trying to convert. And the
So
number,
are we
if you had to take a guess, what's the number you're trying to convert?
the calories?
Which calories?
The 240.
That's correct. You're
Okay.
trying to convert 240 calories. I just wanted you to be confident in your answer. All right, so we write that down, 240 calories. What do we do next?
We do the multiplication and division bar.
Okay. Now what?
We put, I think we're going to put the calories on the bottom.
Correct.
And then I'm not really sure what we're converting that into.
Well, that's the thing, right? That's what we have to be clever enough to figure out. What do we want to convert calories into? Let's take a look at our notes here. Well, we eventually want to convert them into squats, kilogram squats. Do you have a conversion between kilogram squats and calories?
Well, we have a conversion for like the joules, the amount of joules, right? So for lowercase calories.
Right.
The imperial. So would we put the lowercase cal on top?
That's a good idea. Okay. How many calories are in a calorie?
1 kilocal. Oh, so 1,000 and so 1,000 on the top and 1 on the bottom.
Right. There's 1,000 calories in 1 kilocalorie, formerly known as the kilocalorie, now known as the calorie. Anyways.
Yeah.
Okay, you've done that. And now what are we going to do?
240 times 1,000, which is.
What kind of nonsense are you talking to me here? Oh, no. Let's keep going until we get all of our units. We only punch at the end. We punch at the end.
All right. So then are we going to convert the kilocalories to the lowercase calories to joules?
Yeah, we've already converted to lowercase calories.
No, I know, but are we going to convert that into joules now?
Yes.
So then the lowercase c cal on the bottom and then joules on the top.
What's my conversion there?
4.2 on the top and 1 on the bottom.
Okay. Now I've converted to joules. Now what?
I think that's where we can start figuring it out, right? Or
We're not done yet until we know how many kilogram squats.
Okay. So
kilogram squats are a unit. Even though we made it up, it's still a unit.
Okay, so then can we say that 20 joules?
No. You can't say anything that has to do with numbers. You're only allowed to talk units to me. That's the secret of dimensional analysis, Wyatt.
Right.
You don't think by numbers. You think by units.
Yeah. So, so we have joules. So the joules would be on the bottom.
Yep.
And then what we're trying to convert into would be squats. So I guess squats would go on the top. Okay, kilogram squats.
That's what I called it.
Yeah.
All right.
And then so for 1 kilogram squat, there's 20 joules. So would we switch that? Like
I just want to know what number on top and what number on bottom. That's all I want to know. You're doing great.
I'm not. Okay, so bottom, we wouldn't put 20, would we? Or we just put 1 joule at the bottom? I think we just put 1 joule at the bottom.
And what would we put on top?
So my train of thought here would be like a 20th. So like.
Wait, that's nonsense. Look, you don't have to have 1 on the bottom. 1 does not have to be on the bottom.
I think we should put 20 on the bottom and then 1 on the top.
That's what I think we should do too. Which is at least you were about to not mess this up, but you made it like doubly pointlessly complicated because you were going to do 1 on the bottom and a 20th on the top, which is the same thing as putting 20 on the bottom. But whatever. Okay. So you did a great job, son. Now punch them up. Tell me what we get. And I'm going to be mad if it's Austin's number. If it's Austin's number, he's not allowed to play anymore.
All right, I got 50,400.
Okay, so Austin was right.
See, they hated me when I was down.
There you go.
That's a lot of squats. That's probably why I shouldn't eat this thing, right? Do you guys think I have it in me? Do you think I could do 50,000 kilogram squats?
I don't think so.
It would take a while. Suppose I did 1 squat a second. How long would that take?
A whole lot of seconds.
That would take 840 minutes. That would take 14 hours. That would be 14 hours of straight squats at 1 squat per second. Dang, there's a lot of energy in these foods that we eat. Maybe that's why we should exercise more and eat less, you know? Although I really haven't figured that one out yet myself.
Although those are only 1 kilogram squats, we could make it a bit heavier, right? And
hell, even just, you know, you probably burn more energy doing this, which is the secret of jumping jacks, right? So
yeah,
you're also lifting your mass up, right? Which is intense. This makes me think that energy is weird because it can flow through various forms. One moment it's a kilogram lifted off of a ground. The next moment it's in my Cascadian Farms candy bar. Energy is cool like that. It's ghost-like. It's, you know, like in the science fiction movies where they have those aliens that can shapeshift into different forms, a polymorph or whatever you call it. That's sort of what energy is like. It can take all these beguiling forms that surprise you that this is energy and that's energy, and they can actually be converted into one another. There are so many different forms that you have to learn about. Potential energy, gravitational potential energy is just one type. Another type would be kinetic energy. Here's an iconic photograph taken by Doc Edgerton, the MIT physicist, who did cool experiments in photography. And you can see this bullet rupturing an apple. Moving objects, projectiles, things that have mass that move at some velocity, they have a type of energy called kinetic energy. You can think of kinetic energy as, this is the number of joules I have to put into my bullet to make it travel this fast. And therefore, this is the amount of joules it will cost me to make the bullet stop. Clearly, this apple could not stop the motion of the bullet. Kinetic energy comes up in all kinds of applications. You can convert potential energy into kinetic energy. Let's throw that into our notes real quick. KE stands for kinetic energy. The formula for kinetic energy is a classic. 1/2 mass times velocity squared. Where the mass is the mass of your doodah, it could be a little BB, and V is the velocity of your doodah. And we could define it as the energy associated with a moving object. Technically speaking, we define kinetic energy as the energy necessary to accelerate the object up to that velocity. But I think it's just nicer to say the energy associated with a moving object. It has the right flavor of the feeling, okay? We're going to see some uses of kinetic energy going forward. Most things, when you deal with energy, tend to fall into one of two broad classes of kinetic or potential. Maybe I can show you guys a lame slide that will support that argument. Oh, here's a peaceful use of kinetic energy. I could take the moving molecules of a river and I could get them to rotate this turbine, and I could create some electricity, create some electric energy that can power my Nintendo, okay? So potential energies can have different types. Kinetic energies can have different types. Light is something you're going to learn about today. Light is a pure form of energy, which I would say is not entirely kinetic and not entirely potential. It has a little bit of both aspects, and so it's kind of its own class of thing. And then there's concepts like heat and temperature. This was getting thrown around by a few of you on Tuesday, and it's time for us to clean up our act. Let's have a discussion of heat versus temperature. And I think a good place to start is by considering what temperature you cook a turkey at on Thanksgiving Day. So Thanksgiving is coming, and we're going to have to cook some turkey. What temperature do we cook a turkey at on Thanksgiving?
$350.
350 Fahrenheit, right? So the temperature at which you cook your turkey, Stacy, is 350 degrees Fahrenheit. And there's some air inside the oven that's cooking up your turkey. Okay. Now, if you have a big family, you might have to cook an extra turkey. And since your oven's occupied, it might be a good idea for us to, I don't know, maybe for us to boil some turkey, okay? So we'll get some water, and we'll set the water on fire on the stove, okay? And then we'll throw some turkey legs in there. What temperature does the water boil at in the Fahrenheit scale? Does anyone know the temperature of boiling water in Fahrenheit? No, Arunsak, that's in Celsius.
212 degrees.
Nice. So it's 212 degrees Fahrenheit is the temperature of our boiling turkey, okay? Ding! Turkey's done. God, oh, Stacy, did you just, Alexa, none of you knew the temperature of boiling water in your own Fahrenheit system? That's insane. Thumbs down, right, Christopher? Okay, so look, suppose, I think she just hit on me. Listen, suppose one of us had to take the turkey out of the oven, and the other one of us had to take the turkey out of the boiling water. But here's the catch. I'm all out of oven mitts. So one of you is going to have to stick your bare hand into the oven real quick and pull the turkey leg out. And the other one of us is going to have to stick their bare hand real quick into the boiling water to pull out the turkey leg. What job would you rather have? You'll do it, Caroline? Okay, but Caroline, suppose we're going to trade off. Dibs on the oven, says Gianna. I don't know, Gianna. I think you're going to burn your hand, because if you put your hand inside of an oven, right? Dibs on water, says Wyatt. Wait, so Caroline, what do you think? Would you rather put your hand in a 350-degree oven or a 212-degree vat of water? The bubbles don't matter. Oh, are you chatting me? Can I do both at once? I suppose you could. But which one is more dangerous? Putting your hand into 200
Professor, I'll tell you what. Whenever I'm heating up my Tallulah's burritos and I boil them in tin foil and then I heat them up in the oven, when I put them in the oven, I take them out with my hands. But when I put them in boiling water, I have to fish them out.
But how does that make sense? Shouldn't you get a worse burn from the oven at 350?
But I'm not too sure. I just think that the heat doesn't translate as well. I don't know if that makes any sense. But
that actually does make a little bit of sense.
like
but
the
I want to
water,
make
there's direct contact where like
clearly, Caroline. I'm sorry, Caroline, but what you just said is a false statement. The water is clearly not hotter than the oven, because the oven is at a temperature of 350 degrees Fahrenheit. Oh, okay. Now some people are saying some good things. Temperature does not transfer faster through air, Wyatt. I'm afraid you're wrong.
Dang.
Water is a better conduit of heat. Arunsak said something good. A couple of you said the right thing. You guys should try to shout your stuff out if you can. Although I like reading your comments because they're usually really funny. Remember that there's some people who are going to watch these videos later, and I do try to post the chat in the YouTube, but sometimes people don't read it or it gets hard to see. So anyways, just some thoughts about speaking versus chatting. I wanted to see if you guys could figure out the conundrum of why it's more dangerous to put your hand in the water when its temperature is lower. And so far, Arunsak has come up with the best thing. Water is the better conduit of heat. But why should I care about that, Arunsak? Shouldn't the temperature matter? What is let's put it this way. What's the difference between temperature and heat? Emily's Googling it. Does anyone know? No. Convection, okay. Well, it's not the steam. So, yeah, it's about heat is transferred, Gianna. That's right. Let's take a peek at the difference between the how do I want to do this? Let's take a look at a microscopic picture of what's happening inside of your oven, okay? I need to minimize this. Get out of here. I need to minimize this. I want this. So I want slide 2 and I want another slide. I want slide 2 and I want slide 22. That's easy to remember. Function F5. Let's start with 2. The water is made of molecules of H2O, which are all slithering around inside your beaker or inside your pot. And the air in the oven, which cooks your turkey, is in the form of molecules of nitrogen and oxygen, which are kind of floating around. Let's take a look at the molecules that are inside of our oven by floating over to slide 22 here. These could be the particles of air inside of your oven. The red particles represent nitrogen molecules, and the red particles represent oxygen molecules. That's what air is, as anyone who's taken my 1010 class knows. It's a mixture of 77% nitrogen, 21% oxygen. And these molecules are about the same size and similar in mass, and they're bopping around together. And each one of them has a tiny amount of kinetic energy because they are particles that have mass and they have velocity, and there is an energy associated with each and every one of these molecules. If you follow one of the red oxygen pellets, you'll discover that its kinetic energy is constantly changing because it's mosh pitting and slamming into the other molecules. And as it does so, sometimes it picks up speed and sometimes it loses speed. However, if energy is to be conserved in a closed box like our oven, if momentum and energy are conserved, then for every particle that loses speed, some other particle should pick up a little bit of speed. And the ensemble of particles, they should maintain an average kinetic energy, which is consistent. And this, my friends, is what you measure when you measure temperature. Let's start writing that down. Temperature is a measure of the average kinetic energy in a system of particles. That system of particles could be in any state of matter. They could be in the gas state, or in the liquid state, or in the solid state, or in the plasma state. Hell, they could even be in the Bose-Einstein condensate state, which maybe we'll talk about at some point. There's all kinds of states of matter that you haven't heard about. But if you measure all of their kinetic energies and take the average, then you understand what temperature is. Now, we can't actually go and count up all their atoms and measure their velocities. That would be a pointlessly complex task. All we have to do to measure temperature is find a substance that will vary with temperature, like, for instance, the height of mercury in a glass thermometer. And then once we etch a marking on one level and a marking on the other, we've created a temperature scale. In a moment, I'll teach you guys about the 3 temperature scales that we'll use in the class: Fahrenheit, which is the worst of them, Celsius, which is better, and Kelvin, which is the best. But for a moment, let's contrast temperature with heat. Heat, properly defined, is nothing more than a transfer of energy. It's measured in joules, just like energy is. It's a transfer of energy from point A to point B. Point A could be some whiskey, and point B could be some ice cubes. And as energy flows into the ice cubes and causes them to melt, we have transferred heat. Caroline mentioned convection. Convection is one of our 3 modes of heat transport. There are only 3 methods to get energy from point A to point B. Let's write them down because they're going to play a role in this class. The so-called 3 modes. Sometimes they call it the 3 modes of energy transport. Sometimes they call it the 3 modes of heat transport. are conduction, convection, and radiation. Now, I have lots of things to say about these three modes, but I'll wait until the appropriate time to get into the deets on it. For now, I want you to know that there are three possible methods of heat transport: conduction, convection, and radiation. That's it. So, Arunsak, since you had the best answer, why don't you talk to me a bit, buddy? Why do I suffer a worse burn when I put my hand into 200-degree water than in 300-degree oven? In which setup here are the particles moving faster? Are the particles moving faster in the oven, or are the particles moving faster in the water?
I think the particles are moving faster in the oven.
Correct.
But the reason why you're burning more in the water is because you're coming into more contact with the moving particles in the water, since it's more particly together?
Yeah, I think what you said was cool, right down to particly, right? So the way you would look at it, Runsack, is, let's see if I can badly draw a hand here I'll use black and I'll change my line width here. Okay, so can I get this moving again? Oh, I can't draw and have it move. Oops, sorry. So let's go to slide 2 then, and I'll try to annotate to slide 2. When your hand is in the air of the oven, these little particles are flying around like bullets, and they're smashing into your hand. And when they smash into your hand, they transfer energy. That's how you cook the turkey. You cook turkey skin that way, right? When you put your hand into the water, the particles per particle have lower energy and lower velocities. But as Arunsak was saying, there are many more bullets striking your hand per unit time. So it's like getting hit by a million slow bullets instead of one fast bullet. Those millions and millions and zillions of bullets are all transferring energy to your hand, such that you very quickly suffer a burn. Whereas, think about it, how long does it take to cook that turkey on Thanksgiving? It takes hours and hours and hours, because first you have to have those air molecules bounce off the turkey skin, and over a long period of time, the energy has to conduct its way towards the center of the bird. Austin's method of heating up his burrito is actually quite ingenious. By boiling it in water and tinfoil, he can heat it up rapidly, and then he can toast it up in the oven to make the skin nice and crispy. Thanks, Austin. I think I'm going to use that technique when I heat up my leftover burrito today. Okay, let's do a little bit on, yeah, that's a good strategy. Also, the difference between heat and temperature is one of the reasons why, if you've ever tried to cook, like reheat pizza in a toaster oven, if you're reheating pizza on a toaster oven and you leave it in there for a while, if you go to grab the crust and pull it out quickly, you can actually burn your hand pretty bad, because the solid crust is dense and it transfers quite a bit of heat. There's a bit of mass there that transfers heat to your fingertips. But an old trick is to put the pizza on a thin piece of tinfoil, and even though the tinfoil is at the same temperature as the pizza, you can grab the tinfoil and you can pull it out of the toaster oven without burning yourself, because the tinfoil has such a small amount of mass, there aren't enough particles to transfer the heat to your hand. So that's a situation where the tinfoil is in a solid state, but it still can't transmit as much heat because there's such a small amount of particles vibrating there. So those are tricks that all good cooks know. Now, we should take a moment to learn how to translate between our temperature scales. And I've got a little slide here that I'd like us to, to reproduce. Here we go. This is a little scale, a temperature scale showing you the difference between the Fahrenheit, the Celsius, and the Kelvin scale. And I've learned over time that this is a worthwhile thing to take as a note. Let's make a table together. Let's make a chart. This will be helpful if you need to convert temperatures in Celsius and Kelvin back to Fahrenheit, which you're more familiar with. So I'm going to make 1, 2, 3, 4 columns here. Okay. And I'm going to have a number of rows. I'll have one for boiling water. I'll have one for human body temperature, one for room temperature, one for freezing water, and one for absolute zero. So this will be the substance. Let me make sure that you guys can see all of this on the board here. Sorry. This will be the substance. This will be in degrees Fahrenheit, degrees Celsius, and then the scale that I need you to know about, the Kelvin scale, which is what we're primarily going to work in. So we will do boiling water. We will do a human being. We will do room temperature. We will do freezing water. I should have put H2O. And then last, we'll talk about absolute zero. All right, guys, what do you know? You know now that boiling water is 212 degrees Fahrenheit. I sure hope you know freezing water. I mean, you know what temperature water freezes at, right? In the Fahrenheit scale?
32.
All right. If a human being is roughly 99 degrees Fahrenheit, right? Room temperature is maybe 68 degrees Fahrenheit. We'll leave absolute zero alone from now on. Now, Fahrenheit, I don't remember the exact origin of how the Fahrenheit scale was invented, but you'll notice that they pegged a human being to about 100 degrees Fahrenheit, and they did boiling water to 200 degrees Fahrenheit. That's a really goofy way to design a temperature system, because you're using two different thermometric substances, and one of them, the human, is remarkably inconsistent. It's much better to base your entire temperature scale off of water, and that's how Celsius works. We peg the freezing point of water to be 0 degrees Celsius, and the boiling point of water to be 100 degrees Celsius. And that means, let me just check my numbers, but a human is probably around 32 degrees. I'm sorry, a human is around 37 degrees Celsius, and room temperature is around 20 degrees Celsius on that scale. So obviously, if you guys have ever heard the conversion between Celsius and Fahrenheit is like 9/5 plus or minus 32 degrees. So it's approximately true that in terms of temperature differentials, I want you guys to watch how I use my units here. When you talk about changes in, when you talk about absolute temperatures, you put the degree symbol in front of the Fahrenheit. When you talk about changes in temperature, it's customary to put the degree symbol after the Fahrenheit. So I would say for changes in temperature for delta T, a change of 1 Celsius degree is approximately equal to a change in 2 Fahrenheit degrees. So Celsius degrees are twice as fat as Fahrenheit degrees are. These are called temperature differentials. These are called absolute temperatures. People have been measuring temperature for longer than they actually understood what temperature was. It was only through careful experiments done with something called a volume gas thermometer did people slowly start to realize that when they were measuring temperature, what they were measuring is what you see in slide 22 here. They were measuring the kinetic energies of the particles. And they figured this out because they put a bunch of different gases into a sort of volume gas thermometer, which kind of looks like a beaker or something. And no matter what the substance was, whether it was hydrogen or helium or oxygen or neon or whatever, as they cooled the substances down, all of them started to converge towards the same temperature. And that suggested that the particles were moving slower and slower and slower as they were cooling down. In fact, that's one goofy way that we can think about temperature. A useful lie is to think of temperature as the speed of the particles. Eventually, you would get to some temperature that was so cold that in theory, all the particle motion should stop, and there should be no more motion to any of the particles. That's when you reach the theoretical limit called absolute zero. That occurs at negative 460 degrees Fahrenheit, or at minus 273 degrees Celsius. We have managed to cool substances to within a 10 billionth of a Celsius degree of absolute zero, but nature has never actually allowed us to get to absolute zero. Nature gets very pissed off at you when you try to cool something down that much. There's an inherent amount of buzzy energy that's just inherent to particles through quantum mechanics. You can't stamp it all out. The Kelvin scale was designed to improve upon the Celsius scale, with the idea being Celsius is pretty cool, bro, I like it, but what if we just realized that since the speed of the particles is always a positive quantity, what if we just kept the Celsius scale but reset the 0 point to be absolute zero? Then you would start your temperature scale at 0 Kelvin and proceed upwards from there. Freezing water would be 273 Kelvin. Boiling water would be 373 Kelvin. And a human body is around 310 Kelvin, and room temperature is like 293 Kelvin. These are good numbers to memorize because it'll be easier to convert temperatures in your mind if you have a rough sense of what some common useful reference points are. And I think this chart will be nice for you in that regards. Talking about temperature is a nice gateway for us to start discussing those atoms themselves. Does anyone need a little extra time on this, or can I erase it? Runsack, you want some time? Oh, you're good. Does everyone have this down? All right, I'm erasing it. Before we talk about light, let's learn a little bit about atoms. You guys probably already know some things about atoms. Atoms are basically light factories. Light comes from atoms. What do you guys know about the Bohr model of the atom? For instance, if I were to show you this picture here, do you know what you're looking at? Tell me everything you know about this picture.
There are protons and neutrons and the nucleus in the middle.
Right. And?
The protons are positively charged, the neutrons are neutrally charged, and then there's the electrons, which are negatively charged, orbiting the nucleus.
Okay, Wyatt, I like everything you said. Suppose I keep asking you questions. Let's find out where your breaking point is. Why do the electrons orbit the nucleus? What makes them orbit the nucleus?
It's electromagnetism.
Very
right?
Good. It's not gravity, it's electromagnetism. It's the force of electromagnetism.
That's why you can have stable elements or stable atoms.
Well, the stability of atoms in a way also has to do with their stability of their nuclei, right? So we're very quickly going to have to talk about all the four forces of nature. But so far,
you don't have orbits crashing into the nucleus because they're orbital decay.
You know what, Wyatt? I'm gonna tell you something that your chemistry teachers didn't tell you. Sometimes the electrons, they do crash into the nucleus.
But it's not because of their loss in gravity.
Oh yeah, gravity's got nothing to do with any of this. But look up in Wikipedia sometime, look up K capture, And you'll discover from time to time these electrons actually zing right into the nucleus and create little nuclear explosions. It's pretty badass.
That's awesome.
Yeah.
I'm definitely gonna look. What
Yeah,
was
it's
it called?
K-capture. They call it
All right.
K-capture. It's a process where every now and then, they never tell you this in Chemistry 101, every now and then an electron will just zing into the nucleus and create a little nuclear explosion, change the element, all kinds of madness. Wyatt's got a pretty good hang on this thing. Oh, by the way, Wyatt, I was going to ask you one more question. Do you know what atom that is?
That one, 2, 3, 4, 5, 6, 7. What is that like?
6.
Oh, 6. What is that like? Carbon is 7, right? Or is it 8? Fuck. So I don't
Carbon
know.
is 6. You got it
Oh,
right.
it is. Okay.
It's carbon.
Yes.
Carbon is 6. Okay. Let's learn about how he did that, and maybe some of you guys know that stuff as well. Why don't we start with a basic element, not the most basic, but let's start with helium, okay? Helium is the second most abundant element in the universe, and a good place for us to start discussing these things. I like to use those same colors when I draw an atom. So a helium atom has 2 protons in its nucleus, okay? So I'll draw 2 protons. There are 2 neutrons in the nucleus. And then there are 2 electrons which orbit around the nucleus. 2, 2, and 2. Nature just loves a helium atom. It's a noble gas. I'm going to assume that you guys know that these are the neutrons. I'm going to assume that you guys know that these are the protons. I'll assume that you guys know that these guys up here are the electrons. Most students come into my class knowing that, okay? Did you know that these things are sometimes called nucleons? Okay. So these things together, neutrons and protons, are sometimes called nucleons. Nucleons means either a proton or a neutron. So we would say the helium atom has 4 nucleons in it. Sometimes you just want to refer to the doodads in the nucleus without worrying about whether they're positive or neutral.
Yeah.
As Wyatt mentions, atoms are held together by a new force of nature, the force of electromagnetism. Electromagnetism is based entirely on a magical property of particles called charge. And charge is a sort of abstract carrier of the electromagnetic force. There are 2 rules associated with electromagnetism and charges. One is like charges repel. The second law is that opposite charges attract. You should be aware that the fact that there are 2 rules associated with electromagnetism makes it more complex than gravity. Gravity only has 1 rule. Everything with mass attracts. There is no gravitational repulsion, and that kind of sucks because I was totally promised a hoverboard when I was a kid, and I haven't gotten one yet. And I mean the real hoverboard, the one where you like levitate and shit. Yep.
With gravitational repulsion.
Say that?
There's so much more that we could do with
Gravitational repulsion. I know, we could jump over buildings. We could not fall out of airplanes.
like long distance space travel.
Easy, right? Easy. I know. Sometimes I think if I could do anything in science, discovering how to reverse the charge of gravity, that would be the absolute bee's knees. There would be so many cool things you could do.
That would be a good one.
You'd be Spider-Man. You would just jump from building to building. It would be wonderful.
Yeah.
Anyways, we don't have the anti-gravity yet, so we have to just deal with being stuck on Earth. Charges, though, do provide us with the opportunity for repulsion. As you know, anyone who's ever played with a couple of bar magnets and felt that invisible force pushing these things apart. You've felt a force field. Force fields are real, and they're cool, and they're mysteries of nature. In some ways, charge is to electromagnetism as mass is to gravity. Let me show you a cool comparison about the difference between mass and charge in our three atomic particles here. I want to do a little table with you. I need to erase this though, okay? I'm erasing. I think this next table is an important thing to keep in mind. Let's say we wanted to compare our three particles by mass and by charge. So here's the particle, here's the mass, and here's the charge, okay? Charge is sort of like, we say it's quantized. It's relegated to pluses and minuses, plus ones and minus ones. It's integer-like. So here's a proton. I want you to watch how I draw this. A proton's a big fat particle. A neutron is also a big fat particle. But when I draw my electron, I'm going to draw it as sort of a little tiny particle. Now, the mass of electrons are quite small. The mass of an electron is 9 times 10 to the negative 30 kilograms. But so what? We ain't talking about bricks here. We're talking about electrons. They're pretty teensy-weensy, itsy-bitsy. It might be nicer to just refer to the mass of an electron as 1 electron mass. So I'm going to call it 1 ME, and I'm going to define 1 electron mass as 9 times 10 to the negative 31 kilograms. If you were to compare the masses of protons and neutrons, you would discover something interesting. The neutron is roughly 2,000 times more massive than the electron. And weirdly enough, the proton is also roughly 2,000 times more massive than the electron. And that means neutrons and protons are kind of like massive particles in comparison to an electron. For instance, in human terms, I can lift a 1 kilogram mass, but I cannot lift a 2,000 kilogram mass. That would be like two vans, two Dodge Ram vans. I couldn't pick that up with my hands. So a factor of 2,000 is significant in my opinion. That means the electron is like, it's so microscopic and tiny, low mass in comparison to these other particles that it almost doesn't even exist. And yet somehow this little itsy bitsy teensy wincy electron packs an equivalent amount of charge as the proton, albeit oppositely signed. The proton has a charge of +1. The electron has a charge of -1. And neutrons are kind of neutral, so their charge is 0. Now, it is one of the perversities of nature that she made these two lopsided particles that are equal in charge, but totally unequal in mass. And that's pretty freaking weird if you think about it. Whatever mysterious thing is going on inside there that gives it a charge of plusy oneiness is equal to the negative oneiness of the electron. But the electron is a much physically smaller and lighter object. In fact, people have hypothesized, could it be possible that nature could like reverse this equation? Could nature make a little tiny particle that was positive charged? Could nature make a big fat particle that was negatively charged? It turns out the answer is yes, she can. And she does. And we find this so-called antimatter inside of particle accelerators every day. So we live in a world where there are lots of positively charged protons and negatively charged electrons, but it could be that there are other places in the universe where antimatter is more common than matter. We'll get to that stuff later. For now, let's learn a couple of terms that you're going to need to know, both for our homework today and just for life and for science's sake, okay? I'm going to erase this so I can define some terms for you. let's start by defining the letter A as the atomic number associated with your atom. The atomic number is the number of protons in your atom. What is important about the atomic number is the atomic number defines the element, which is the same thing as saying defines the atom. This is actually not an unimportant point. This point matters because sometimes when atoms get split apart, it can sometimes get difficult to identify which atom you're dealing with. By counting the number of protons, you know. For instance, if I wanted to, I could introduce you to a friend of mine known as the periodic table of the elements. The periodic table of the elements shows you the totality of all the different atoms which exist in nature. And each one is separated from each other one by the atomic number, which is shown up here in the corner. The atomic number tells you the number of protons. We discussed earlier with Wyatt that carbon has 6 protons in its nucleus. I'd like to go back to a thinner, more colorful marker choice, okay? Next up, we have something called the mass number. We'll use capital M for mass number, although people do different stuff for this. We're going to keep it simple. This is the mass number. The mass number is the number of nucleons in your atom. That means it's the number of protons plus the number of neutrons. The importance of the mass number is that the mass number defines the isotope. Who knows what an isotope is? Wyatt, tell us. Lay it on us.
It's a specific version, I guess, of an atom with a specific amount of electrons that orbit. Like it can
You were
have the
doing
same.
good until you were doing good until you said electrons. Once you said electrons, you were false.
I only know because if you add 2, or is it? Maybe I don't know. Because I know like tritium is the what they put in watches, the stuff that glows.
Tritium.
And that's like, yeah, tritium, and that adds. Does that add 2 protons?
Daniel DaCosta figured it out in the chat. He reminded us that it's the number of neutrons that varies. It's not electrons, Wyatt. You can change electrons all day long. Isotope means same number of protons, different number of neutrons. Hey, what's the job of the neutron anyways? I can have different numbers of neutrons? Does anyone care about neutrons? Are neutrons just there, or do they do something? What the hell does a neutron do anyways? No? Nothing?
Some sort of balance, equilibrium.
Balance to what?
No idea.
Well, let's remember our 2 rules of electromagnetism. Our rules of electromagnetism were like charges repel and opposites attract. Now, the electrons are sure attracted to the protons. That's one thing, but look at all these protons in the nucleus. They're smushed up against each other. And protons don't like to be smushed up against each other, right? Trying to smush 2 protons together is the same as trying to force 2 north ends of a magnet together. They don't like it. And yet somehow you force them to smush all into a tiny volume of space called the nucleus. Electromagnetism cannot explain what's happening here. If it was up to electromagnetism, the carbon nucleus would fly apart and self-destruct, and then no living organisms could exist in nature because their atoms would just decay. The neutron does provide a job. It provides a glue that allows the protons to hang out with each other. It does this by means of a new force of nature called the strong nuclear force. The strong nuclear force binds the quarks that make up protons and neutrons together into a cohesive nucleus. Chemistry is the study of electrons bouncing between atoms. Nuclear physics is the study between the change of protons and neutrons in the nucleus. They are different levels of craziness. Isotopes happen because sometimes you can tinker with the number of neutrons and still keep your nucleus stable. Hell, you can even have unstable nuclei, such as uranium-235. Most atoms are electrically neutral. When an atom is electrically neutral, its electromagnetic forces are balanced. And that means same number of protons as the number of neutrons. I'm sorry, same number of protons equal to the number of electrons. Apologize. From time to time, you can rip an electron off of an atom, or in some cases, push an extra one onto it. That's when you develop an ionized atom. An ionized atom is where you remove, or in some cases add, electrons. When you do so, you create a fourth state of matter known as a plasma. A plasma is basically just a charged gas, like a sea of protons and electrons that are not connected to each other. Let's get all that down into your notes. That's going to be important. Cations and anions. Hell yes, Daniel. It's good stuff. I need some iced tea. Sorry, guys, I was fiending for a hit of unsweetened iced tea here. Can I erase this? Let's play a game. Let's build an atom. Unsweetened. Arunsak, the only good iced tea is unsweetened iced tea. Why would I want to pump all those? Didn't we do a lesson about calories earlier? You think I want to be doing kilogram squats all day? Besides, I just want the drug. I want the caffeine in its raw, unbridled form. It's delicious. Okay, let's build an atom. It's a game. It's a game to help me make sure that you understand what the F I'm talking about. Well, maybe that's where the granola bar comes in, Kevin. Okay, so this atom has an atomic number of 1, it has a mass number of 1, and it's also electrically neutral. Who can tell me what this atom looks like? Let's find a studio volunteer, like Emily. I want to hear those parakeets. What's going on, Emily? Can you help me build this atom? Oh, did you just hide from? Oh, there you are.
So no parakeets for today.
Oh.
Yeah.
So let's walk through this. Let me tell you how to do this, Emily. Use your notes. What does atomic number of 1 mean, according to your notes?
The number of protons.
So how many protons do we have?
1.
So I will draw 1 proton. That's how we play this game. Okay, what does the mass number mean?
The number of nucleons.
Okay. So how many neutrons
So
should
it's
we draw? Did I trick you? Are you tricked?
I
How
don't
many
know what I'm doing.
neutrons?
Is there even any way to tell how many neutrons there are?
Yes. If I specify the atomic number and the mass number, you should know the number of neutrons. You got to think through this, though. You know there's one proton, and you know there's one nucleon. So how many neutrons do I have?
None.
Very good. I did not trick you. And I'm a little disappointed I called on you now, to be honest, because I was hoping. That's right. There's no neutrons because you've already used up your one nucleon, didn't you? What about the electrically neutral business? What does that mean?
Same number of protons equals the number of electrons.
So how many electrons do I have in this atom?
I'm not sure.
Yes, you are. It tells you right there. The number of protons is equal to the number of electrons. How could you not know?
Is it just one?
Yeah. If the number of protons is equal to the number of electrons, it's got to be one. You have built an atom successfully. Do you know the name of this atom? Daniel does. Hydrogen. This is the most famous atom in the entire universe. Okay, Daniel, since you're so good, Paul G, since you're so good, you know about hydrogen, you know about the kaboom atom. Listen, what is the name of the isotope of hydrogen? Does anyone know the name of the isotope? Didn't think so. That's where I got you, huh? Daniel? Paul? Well, you can call it H1, but that's kind of lame. This is a famous atom, a famous isotope. It's called protium. Okay. Caroline, you're the next contestant on Let's Build an Atom. This atom has an atomic number of 1. This atom has a mass number of 2, and it's electrically neutral. What does my atom look like, Caroline?
There's one proton.
Correct. What else?
One electron.
Okay. Is that it?
And there's one neutron.
Correct, because we need 2 nucleons and we've only used 1 nucleon. Do you know what this atom is called, Caroline?
No.
Well, what did you learn about the atomic number? Tell me some things about the atomic number.
The number of protons is equal to the atomic number.
And unfortunately, Paul, that's not correct. No, Caroline, keep going. What else does it say about atomic numbers?
It defines the element.
So it defines the element.
There's
Daniel,
one proton.
see, Caroline, if the atomic number is the same and the atomic number defines the element, then
yeah,
it's got to be the same element. It's still hydrogen. It's just a different isotope of hydrogen, as Daniel DaCosta points out. Daniel, do you know the name of this isotope? This is probably the most famous isotope in all of nature. Deuterium is correct, Daniel. This is what isotopes are all about. Same number of protons, different number of neutrons. Well, I'm just trying to point out, Arunsak, that there are some details about atoms that not all of us have worked out. We're going to talk about why the universe is cold. You might actually rather ask the question, why is the universe so warm? Let's take a tiptoe out into the universe, since you all are so curious. Let's go somewhere magical, like the Eagle Nebula. Let's take a trip to the Eagle Nebula, shall we? Let's float through outer space. Let's get this hair out of my mouth. Okay, here we are, and we've taken a ride in the Millennium Falcon, and now we are in the Eagle Nebula. Look at all this. This is a pretty high-resolution picture, so it's going to take a second to load. Really need to get some faster internet up here. Just bear with me, guys. I'm trying to make a point. Wow, if it's loading this slowly on my computer, it's got to be loading really slowly on yours, huh? I ain't got time for this fool nonsense. Okay, fine. We'll go somewhere else. Let's go to the Pillars of Creation. The Pillars of Creation are actually in the Eagle Nebula. Could someone just give me a bloody picture of space?
Space is canceled due to coronavirus.
Yes, okay. All right, fine. I'm finally in the Eagle Nebula. Let's fly through the Eagle Nebula on our magical spaceship, okay? Suppose I were to take like a cosmic vacuum cleaner, and I were to just start sucking up gas out of the Eagle Nebula, and I started counting up all of the atoms that make up this gas. You know what I'd find? I'd find 9 out of every 10 atoms was a hydrogen, and 1 out of every 10 atoms was a helium. So basically, all of this gas is 9 hydrogen atoms for every 1 helium atom. And that's mostly what it is. There's occasionally an atom of carbon or nitrogen floating around, but they're really rare. You have to count through thousands and thousands of atoms before you find a carbon. And if you want something more exotic, like, I don't know, titanium, forget about it. You got to count through hundreds of thousands of atoms. For the most part, this gas is all 9 parts hydrogen to 1 part helium. Suppose I were to just throw away the helium atoms because they're boring, and I were to sift through the hydrogen atoms. I would have to collect 6,000 protiums before I came up with 1 deuterium. That is, in nature, in the Eagle Nebula and everywhere else that I go, I find 6,000 normal protium hydrogens to every 1 deuterium. And I find that all over the universe. Even the bloody hydrogen in this iced tea, the water molecules of this iced tea, I'd have to count through 6,000 water molecules, or since you get 2 atoms, I'd have to count through 3,000 to find 1 deuterium. This is what is known as the cosmic abundance of deuterium. And that deuterium, my friends, has been left over from the Big Bang. There was something about the conditions in the Big Bang that created this tiny sliver of deuterium, which still exists in nature today. Nature creates certain amounts of isotopes and just litters them throughout space. Sometimes they're forged in stars, but in the case of deuterium, it's really cool because it wasn't stars that did this. It was the Big Bang that did this. Sometimes people study the fraction of deuterium to learn more about the conditions in the Big Bang. Isotopes are cool. Let me take my last moments. I want to do one last thing here. I kind of need to push into a discussion about light because part of your homework today is working with atoms and part of your homework today is working with light. And I'm kind of running out of time, so I'm going to have to give you some uncomfortably quick notes here. Let's take a look at a model of light and where it comes from. If I were to do this sort of the quick and sort of fun way, I would say that inside of atoms like hydrogen, excuse me, my slides are kind of hurting here. Here's a hydrogen atom, and here you can see electron orbiting around it. As you may have learned in your chemistry class, the orbits of electrons are quantized. Normally, the electron orbits the proton at this distance here, which is a short little distance. It's like a 0.05 nanometers. And the electron is typically found really close to the proton, orbiting in what's called the ground state or the lowest energy orbit. But sometimes you can energize an atom and you can give the electron some extra kinetic energy, and you discover that the electron can orbit at farther distances, but only pre-proscribed ones, like grooves on a record, okay? The electron can orbit here at the ground state. The electron can orbit here at the first excited state, but the electron is not allowed to orbit anywhere in here. That's because in atoms, you're not dealing with the large macroscopic world of space. You know, if this were the sun and the earth, you guys know that the earth orbits from the sun at 1 AU. But there's nothing in the laws of gravity that would prevent the earth from orbiting at 0.7 AU or 0.6 AU. The earth, in theory, could kind of orbit at any distance it wants. That's because on a large scale, space is smooth and continuous. When you get down into the world of atoms, quantum mechanics takes over. And quantum mechanics teaches us that the world of atoms is kind of pixelated or quantized. Electrons can exist at this position, they can exist at this orbit and this orbit, but they can't travel in between. However, it does take energy to push an electron from one orbit to another. Usually the way you give an electron energy is you smash it with another atom and the electron gains a little kinetic energy. The electrons will orbit at the higher orbits, but when they drop back down from a high to a low orbit, they release a tiny little packet of light known as a photon. And these are the kind of things that we're going to start by thinking about. We're going to think about what is light. Light is, technically speaking, an electromagnetic wave. I'm going to put this as a note on the board in just a second. But first, let's have some pictures. Light is a wave of electromagnetic energy. And what this is here is these are representations of the electric and the magnetic field. If you've ever taken two bar magnets, and if you've ever pushed the two north poles against each other and felt that invisible resistive force, then you have felt the magnetic field. Can you see it? Hell no, it's invisible. You can't see the magnetic field, but you can feel it. It's real and it's there and it's kind of magical, right? Well, light consists of ripples, which are one part electric field and another part magnetic field. And these ripples travel through space, and sometimes they come in little tiny packets called photons. Let's start by taking some notes on this because we're going to need it for our homeworks in a few moments. Okay. Oh, please don't hold back your enthusiasm. I love it. All right. So light is an electromagnetic wave. It consists of one part electric field and one part magnetic field. I don't have time to get into the differences, but I'll use a one-word description to help differentiate these. The electric field is associated with static charges. Static charges are protons and electrons which are not moving. Pulling socks out of a dryer, when you hear them crackle, that's the electric field. When you wrap your burrito in saran wrap and the rubbery saran wrap sticks to your burrito, that's also static charges. It's also one part magnetic fields, and magnetic fields are associated with moving charges. Currents traveling through wires. Bar magnets have moving charges, but that's a little bit tricky to understand. Usually, we don't draw the electric and the magnetic fields unless you have really talented arc skills. You'll notice in my diagram here that the electric and magnetic fields must always be pointed perpendicular to one another. And they kind of oscillate and travel through space, kind of like this, okay? This is a more sophisticated picture of light. These fields are actually an example of something called a vector field. But vector fields are over your pay grade. You're not ready for that yet. Usually when I draw light, I'll just draw it like this, some kind of a wave, and we assume that I'm referring to maybe the electric field, and the magnetic field is hidden in there somewhere. Light can actually take the form of tiny packets. And the tiny packets of light are called photons. You can think of photons as particles or packets of light. They act like particles and waves, okay? A photon is kind of like a tiny piece of light. A good analogy is that a photon is to light as atoms are to matter. If we say that matter is composed of these indivisible nuggets called atoms, waves of light are composed of individual little packets called photons. Sometimes people represent photons as a little localized wiggling wave, something that looks like this. That's an example of a photon there. Now, we're going to need 3 informational pieces. We're going to need 3 bits of knowledge about photons before you guys are ready to do your homeworks today. I need to erase this, okay? Okay. Because light and because photons are made of waves, we have to discuss the properties of waves. You need this for your homework in a moment. There are 3 properties of waves that we need to know. One is called the wavelength. The symbol for wavelength is the Greek letter lambda. It looks like an upside down Y, okay? Wavelength is the distance from crest to crest of your wave. It's a physical repeating distance, and it's measured in units of meters, and sometimes it's measured in units of nanometers. A nanometer is defined as a billionth of a meter. You'll need this conversion in your homeworks. Another property that waves have, Arunsak, that sounds good. You'll be able to clean up the rest. Last time I didn't get the video posted until quite late. I'm gonna really work harder to do that better. So anyways, we'll try to get as much as, today's homework is not long, okay? But let me finish this so that we can use it in our homework. F stands for the frequency. Frequency are the number of cycles per second of your oscillating wave. Because cycles are a dummy unit, the real unit of frequency is per seconds, or inverted time, 1/seconds. And we define a per second as a hertz. The third thing that we need for properties of waves is E, which is the energy. So we have wavelength, frequency, and energy. At least 3 of your homework problems today are going to be based on these properties of waves. These 3 properties are related to each other by 3 crucial formulas, which I'll smush up here. One is the speed of light is its wavelength times its frequency, where C, the speed of light, has a fixed value of 3 times 10 to the 8 meters per second. The other formula that we need is the energy of a photon. The energy of a photon is another number from nature called Planck's constant. Planck's constant has a value of 7 times 10 to the minus 34 joule seconds. So this is the speed of light. And this is a constant called Planck's constant. Taken together, these formulas, I'll call this number 1 and this number 2, can be used to relate a piece of light's frequency, energy, and wavelength. I, of course, have to teach you more about these concepts, but for now, I'm just going to leave it there. Okay, it's 1:03. I unpleasantly squished in some deets about light that we'll need for our homeworks. Do you guys want a little break before we tackle the homework so we can carb up? Yeah? Okay. Break. Yes, please. Caroline, what's the kitten's name again? Did you say it was like Mittens or something, or what was it? Paris, that's right, okay. Paris wants a little break, doesn't he, she, whatever the hell it is. Okay, I'm gonna pause the recording. Okay, everyone, welcome back. It's time for homework number 4, which I believe are problems from chapter 5. Let's see what we got going here. Austin, I can only go as fast as you guys can go. And since you're a troll, you're really not doing us much good at all, are you now? We need the problems. Does anyone have those problems queued up? Let's take a look here. Okay. On our papers, we're going to have our name. Put AS1020 and your section, whatever it is. Let's do homework number 4. Chapter 5, numbers 43, 52, 54, 56, and 57. Arunsak, are you down to read one for me, buddy?
Yeah, I'm gonna go pull it up on Blackboard right now.
Okay.
Chapter homework number.
I gave you the problems right there, right?
Number 43. Atomic terminology practice 1.
Oh, hold on. Go ahead.
All right.
Arunsak.
This is A. The most common form of iron has 26 protons and 30 neutrons. State its atomic number, atomic mass number, and atomic number of electrons.
Wait, sorry. Can you repeat that one more time? The iron has 26 protons, 30 neutrons, and then what do they want again?
State the atomic number, the atomic mass number, and number of electrons.
Can you do that for us, Arunsak? That seems pretty
Hold
easy
up.
to me. Does that seem easy to you?
I just gotta write this down.
Yeah. Write it down because you're reading. How about someone else out there? Well, while Arunsak writing that, let me hide the trolls here because they're useless. Hide the non-video participants. Mostly useless anyways. Okay, Wyatt, What's the answer?
All right, so the atomic number would be 26.
Correct.
The mass would be, would it be 56?
That's right. It's
Okay.
30 plus 26 is 56. 56 nucleons. And the number of electrons?
26.
Because it's neutral. Excellent. Okay, Arunsak, what does part B say?
Okay, consider the following 3 atoms. Atom 1 has 7 protons and 8 neutrons. Let me know when I can move on to atom 2.
Okay.
Atom 2 has 8 protons and 7 neutrons. And atom 3 has 8 protons and 8 neutrons. Which 2 are isotopes of the same element?
You want to take a moment to write that down, Arunsak?
Well, can I just answer it?
Yeah. Can you?
Yeah, so 8 protons. Aren't they supposed to have the same neutrons and
No. Look at my
the same
definition.
protons?
Yeah, so which are isotopes?
I'm trying to read this. They all have different protons.
Well, not exactly.
Oh, no. Atom 2 and atom 3 are isotopes.
Yep, and Gianna got that
protons.
as well in the troll house. These are isotopes. Do you guys know what these atoms are? Who's good at chemistry? Who's knowledgeable about the elements? What atom is this? What atom is that? These 2 are oxygen, yeah. Do you know what this one is? That one's nitrogen. So this is oxygen 16, that's oxygen 15. Okay, Arunsak, when you're finished writing, let's get part C down. If you guys want to move quick, then you got to move quick with me. I can move as fast as you can move.
Oh, dang. I didn't finish writing A.
No, just take a moment to finish it.
No, you erased the thing I was trying to write down.
Oh, I thought you had that.
No, I was reading a lot, so I couldn't write it down. All good. I'll find somebody else. You want to read C right now?
Yeah, let's do it.
All right. Oxygen has an atomic number 8. How many times must an oxygen atom be ionized to create an O+5 ion? How many electrons are in an O+5 ion?
Okay, make sure you take a moment to write that stuff down, Arunsak, okay? The answers to the first parts were pretty simple, if you ask me. It was 26, 56, and 26, so you should be able to get that pretty quick. Okay, if oxygen starts off as electrically neutral, and then it's ionized to become a +0.5 ion, how many times did you ionize that oxygen atom? Someone besides Arunsak. Doesn't anyone else there want to share video with me besides Caroline and Wyatt? There's so many of you. Who are you people? I've never even seen you before. Caroline, do you know? Caroline says 5. You are correct. So how many electrons are left over? That should be pretty simple, right, Caroline? No. An O+5 ion still has electrons. Yes. The universal symbol for electron is a little e with a minus sign next to it. Okay, that's number 43. Let me know when I can erase here.
All right, so wait, why does it have 3 electrons left? I guess I'm confused on that part.
Sure, that's fair. For an oxygen atom to balance the number of protons, it has to have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. If it has a net charge of +5, that means you have to take 5 electrons and rip them off the atom. 3 are left
Okay.
behind.
Okay.
Did that help?
Yes. Yeah, I get it now.
Okay. You
I
rip
guess I was
those
just
guys
confused.
right off the electron and you throw them away. You rip them off the atom and you throw them away, rather. Okay, I want to erase.
Don't erase C. Don't erase C.
Okay, move quick. Everyone's always like, Brendan, this takes so long. Well, what takes so long is you guys, not me.
I'm good.
All right. Caroline, will you read 52?
Oh, 1 second. Human wattage. A typical adult uses about 2,500 calories of energy each day. Use this fact to calculate the typical adult's average power requirement in watts. In 1 calorie equals 4,184 joules.
1 kilocalorie. Let's just call it 4,200 joules. I don't feel like doing this problem to 4 sig figs. I meant to include this in today's discussion of energy, but I didn't get back around to it, so I'm happy to tell you now. Power, which is a physics concept, power is defined as energy per unit time. You should think of power as a flow of energy. Power measures the flow of energy through a system. The units of power in the MKS system are the watt. 1 watt is equal to 1 joule per second. However, because calories are a unit of energy, and because days are a unit of time, your calorie requirement of 2,500 calories per day is also a power. That means you are the equivalent of a light bulb. You require a certain amount of energy to shine. And we want to figure out how much energy that is. How should I do it? What's our technique called?
Dimensional analysis.
Hell yes. Hell yes, Gianna. Wyatt, you rocked at this before, so let's have you do that again. We'll get through this nice and quick.
All right.
What do we start with here?
I think we're starting with our 2,500 calories per day.
Excellent. What do we do next?
The multiplication division bar.
Excellent. What do we do next?
Calories on the bottom.
The most flickery bulb. I don't think you're the dimmest, Christopher. I've seen worse. What's, sorry, Wyatt, can you do that one more time?
We put calories on the bottom,
Yep.
and then the small calories on top.
The book has suggested a method of us skipping this. We could do the small calorie thing, Wyatt, but remember the capital calories are the same as kilocalories. And we've got a direct conversion to joules there, so let's use that.
All right, so then, yeah, we'll do joules and then 4,200 on top and then 1,000 on bottom.
Be careful here. Is that what it says?
What's 1 kilocalorie? And we only put calories on the bottom, right?
Look, man, don't blame me. Blame the FDA who did this to you, okay? The National Association of Dumbass Americans decided that you could not handle seeing the word kilo in front of your word calorie on your food packaging. So this calorie, which is a putative calorie, it's actually a kilocalorie. This is why it's confusing. So notice how I use
1 on the bottom.
Yeah. I'm sorry, that's the FDA's fault, not mine, okay? I probably should have told you about the lowercase calorie, but I did. I made that mistake. Okay, what do I do next, bud?
Then we're going to have to do that joules into watts.
Hold on. You cannot convert joules into watts because joules is an energy and watts are a power. What are your current units, Wyatt? What are your current units here?
Would end up being joules per day.
Correct. But a watt is defined as?
A joule per second. Okay.
So what are we going to do about that?
Should we multiply? So, like, we're trying to get to seconds now. So, I don't know how many seconds are in a day.
Well, let's not worry about that. First, let's just start with our units. If you don't know the number of seconds in a day, then you shouldn't be converting from days to seconds. You should convert from days to some other unit. Yeah.
So then we can put, I guess we would just put hours on top and then days on the bottom. And then, so 1 day on the bottom and 24 hours up top.
Is everyone cool with that? I don't think Arunsak likes what you're doing. Oh, you give your thumbs up then? You are cool with that? Maybe I should just let you all get the wrong answer, I guess. Gianna, do you have a problem?
Should day be on top and hour on the bottom?
Who said that?
That was me, Paul.
Oh, Paul. Yeah, Paul. Can you explain that? Because I'm not sure everyone followed that there.
The reason you want to do is you want to cancel out that unit. To do that, one of them has to be on top, the other one has to be on the bottom.
Right. See, Wyatt's used to thinking, whatever I want to get rid of, I want to put on the bottom. But the problem is he's forgetting that the days are already on the bottom. That will lead to units of joule hours per square day, which doesn't sound very pleasant. Paul's correct. Day needs to be on top this time, Wyatt, and hours on the bottom. Remember, this is our motivation. Where are you? I've lost. Wait, I got to hide the trolls again. Video settings, hide the trolls. Sometimes I keep turning the trolls back on just to see who's out there. Wyatt, do you see what happened there, bud?
Yeah. Yeah, I get it now.
Okay, so keep going then.
Are we going to keep, so we're going to keep putting hours on the top now because we're going to keep dividing, right?
Yeah, that sounds like a plan. We're going to have to.
Okay. Yeah. So then hours on the top and then minutes on the bottom.
Right. And then what?
Put in 1 on top and 60 on the bottom. I guess if we're not doing numbers yet, then we're just going to do minutes on top and then seconds on bottom.
When I do these things, Wyatt, I usually get all my units in place before I put the numbers in.
Okay, that makes sense.
That way you're kind of just focusing on the unit business. Okay.
And now we're at second.
Yep, so
now we
can
can
all the conversions here.
One up top, 24 on the bottom.
Keep going.
Oh, 1 on top and 60 on the bottom, and then 1 and 60 again. 1 over 60.
Okay, punch them up.
How many sig figs did we say we were going to? 2.
How many sig figs went in?
2.
So that's your answer. So what'd you get?
130 joules
130.
per second. Is that wrong? Oh, 100 and okay, never mind. My number was wrong.
Do I have to do this? Because if I have to do this, you're fired.
120. I just wrote it down wrong. 120 once I rounded.
What are the units?
Joules per second.
Which is also the same thing as
Watts.
in other words, this is you. This has the same power requirements that your body does. This is actually a 120 watt light bulb. I shit you not. A little brighter than your average light bulb. I use it for some of my experiments and demos. Lit. I like it, Gianna. Okay. Let's get all that copied down. I'm trying not to break my light bulb here. Can I erase? Okay. I don't hear anyone objecting, so I'm erasing. Wyatt, I can't remember who read what so far. Did you read one, Wyatt?
No.
You can, in some ways, you can power light bulbs by coffee and cinnamon toast crunch. What you do is you get one of those. Wait, do I have one? I think I even have. Oh. Somewhere. Oh, yeah. Are you ready? I give
I'm
you light powered by coffee and cinnamon toast crunch. Oh. Damn it. This would have been really cool if it worked. Oh, there we go.
Yeah.
See?
That works.
10 power light with cinnamon toast. Coffee, and in my case, I ate a chorizo burrito. All
It's
right.
just a lot of extra steps.
Yeah. Cinnamon
It
toast.
really is the best.
Cinnamon toast crunch is sugar for breakfast. It's sugar.
Yeah.
It's like sugar bombs, you know? All right.
What else would you?
Wyatt, can you read number 54?
Yes. Radio station. What is the wavelength of a radio photon from an AM radio station that broadcasts at 1120 kilohertz? What is its energy?
So 1120 kilohertz, that sounds like what kind of a quantity? I like my font here. Let's draw a radio tower, okay? Put some support structures in here. Let's put a little blinky light up on top. You know, electric fields come from electrons. To build a radio tower is simpler than you might think. You just got to get a big, stupid pole of conducting metal, And then you burn some fossil fuel and you hook some electrons up to it. And you send some electrons up the wire and down the wire, up the wire and down the wire. In fact, you do it at 1120 kilohertz, or some number of cycles per second. And then a big, long-ass radio wave comes out. In fact, I'm going to make the radio wave red for symbolic reasons. Never draw a radio wave in blue. Our goal is to find the wavelength of this radio wave and the energy. To do that, I'm going to need some formulas. Some formulas that I gave you at the end of lecture. What are the formulas?
You got C equals lamb times F.
Correct.
The other one is E equals H times F.
Okay, where should we start? How do we beast this?
We divide C by frequency to get the lambda.
Okay, I like it. Frequency, wavelength, and C are all on top. So I'm going to take the frequency, I'm going to drop it down below, and then I'm going to flip it. So I get wavelength equals speed of light over frequency. So far, so good. What do I do next?
Now you fill in the numbers. C is the constant you gave us.
Yeah, what's the speed?
3 times 10 to the 8th power meters per second.
So far, so good. And what next?
The frequency is 1120 kilohertz.
I am not feeling that. I am not feeling kilohertz in that denominator. Let's remember what, this is a frequency. You've correctly identified this as your frequency. But what are our MKS units of frequency? Is the per second or the hertz? This, you can think of it as cycles. Yes, Devin. Think of it as cycles per second. So what are we going to do about that then?
Dimensional analysis.
Yes, sir. Yes, sir, Bob. So I've got 1120 kilohertz. What do I do next?
X bar.
Yep.
Kilohertz at the bottom, hertz at the top.
Yep.
And 1 up top, 1000 on the bottom.
Punch them up. What do you mean, Devin?
1.12 hertz. So then you're gonna put that at the bottom, 1.12 hertz.
I'm almost tempted to let you guys do this and then take a point off of everyone's homework. I'm really thinking about that. The hertz cancel out, or actually the hertz doesn't cancel out, Gianna, kilohertz cancels out. That's not the issue. That part is cool. The units.
1,000 on the top.
Yeah, I was waiting for someone to notice that.
How did I do that? Oopsies.
That's okay.
That's me.
The reason, see, I'm trying to dramatize this point because people do this all the time. It's very easy to make this mistake. It's 1 kilohertz is 1,000 hertz. So how many hertz do I have here?
Um, 1.12 times 10 to the 6.
Fine. And that's what we're going to put into the denominator here, because that's the same thing as 1.12 times 10 to the 6 cycles per second. Punch them up. What you got? Don't be shy. Time is money.
Two. Oh wait, we're only doing one.
Oh, actually, believe it or not, the speed of light is good to 3 sig figs. There's
Okay,
no
better
math.
then.
Alright.
It'd be 268 then. 200 and the units would be meters.
Yeah, per seconds cancel out. And a wavelength should be a length, right? Box that
Yeah.
up. I need to erase the conversion down here, guys. Okay, now we find the energy. The energy is Planck's constant times the frequency. Planck's constant is really roughly 7 times 10 to the minus 34 joule times seconds. And now we'll multiply by the frequency 1.12 times 10 to the 6 hertz. What you get? Seven times 10 to the negative 28. Okay, Arunsak, this will be on record for you. Please do it right, okay? All right, bye, buddy. I got you. Christopher, what'd you get? Geez, I'm gonna have a seat here while I wait for you slowpokes. Can you read it? Can you say it to me, Christopher? Can you say it loud, say it proud? Paul says 7.8.
Wow.
I don't see any units, Paul, so I can't accept your answer unless there's units. What do you get, Christopher?
I got the same thing.
I want some units. Yeah. 7.8 times 10 to the minus 28 joules. Okay, Christopher, keep that mic ready. You're going to have to read a problem for me.
Oh wait, why do we do 2 sig figs there?
Well, here's why. This has 3 sig figs. That has 1 sig fig. It's all kind of fucked up, so the hell with it. Honestly,
Okay.
Wyatt, this is me breaking the rules that I so carefully taught you, okay?
Okay.
The
I
real
just wanted to
value
make
of Planck's
sure we're on the
constant
same
is 6.63. Did you watch Stranger Things? The value of Planck's constant to 6 places was part of the plot point of season 2. That girl, the
Really?
chick off the radio tower, she had to know what Planck's constant. They had to open a safe, remember? And in order to open the safe, they had to know Planck's constant to 6 significant figures. And that cool nerdy radio chick, she knew it. I only know it to 3, so she's better than me. I know 6.63. I don't know.
I only know pi to a bunch of digits.
Oh, are you the one who said you do it to 10 digits or something?
I can do it to like 24. Something,
Wow, that's
28
cool.
maybe.
I can do 3.14159265354. After that, I crap out.
3.141592658358979323846264338.
That's pretty damn good. That's impressive. Get a good memory, son. I think Weird Al Yankovic made a song about this. And it's called White and Nerdy. Anyways, here's Planck's constant. We could have used all these sig figs. Sometimes I just say 7 because I don't care, you know. Anyways, I kind of broke the rules. I left 2 sig figs in there, but I should have rounded it down to 1. Okay, are we ready to put this problem to bed? Christopher, I want your help reading number 56, if you don't mind. I'm erasing, by the way. If you have an objection, tell me now.
Okay, just give me a minute to pull it.
Oh, I see. You're just needing a minute to read, or?
Okay. 56.
All right. What's it say?
X-ray photon. What is the wavelength of an X-ray photon with energy 10? The fuck is that?
It's KeV, kilo electron volts.
Wonderful.
Just say KeV. That's how the physicists say it.
KeV. What is its frequency? 1
Christopher.
electron volt equals 1.60 times 10 to the negative 19 joule.
Christopher, I want you to help me do some dimensional analysis. Let's convert the energy into MKS units, shall we? So I'm going to start you off, Christopher, with 10 KeV. I'm also going to make a division bar to speed things up. What units should I put in here, Christopher? Christopher, what are MKS units of energy?
Electron volts.
Electron volts are units of energy, but they're not MKS units of energy. Okay, do you know what units I should put here?
No.
Does anyone see what the problem is?
It gives you a conversion thing at the end. Or you also should probably switch into the EV, not KeV. So
That's
you should
the
have,
first step, sure.
yeah.
So tell me what to write.
Oh, yeah. So then you would write 1,000 EV on top, and then
no numbers until your units are in place.
okay, EV on top, KeV on the bottom.
That's what I wanted to hear. Now what?
You can do another multiplication bar.
Yep.
On top would be joules, and on bottom would be EV.
Wyatt, you are speaking my language. I can taste my after-work beer in my mouth already because of your skill and proficiency at dimensional analysis. Okay, tell me the numbers to put in.
For the first bar, you would put 1,000 on top and 1 on the bottom.
Right, because a kilo is always 1,000.
Yep, and then on the second one, it's going to be 1.6 times 10 to the negative 19th joules, and then on the bottom, you're going to have 1 EV.
Punch them out. Actually, Wyatt, come on, let's be a big boy here. We don't even need a calculator. That's
Yeah,
negative 19. How many zeros are you adding?
3.
Count again.
Oh, 4.
Okay.
Wait,
So negative
yeah.
19 plus 4, what do you get?
1.6 times 10 to the negative 15th.
Good. That's joules. Okay, that's cool. You don't even need a calculator. It's so damn good. All right, so now,
Is it?
do you want to
Never
find the
mind.
wavelength or the energy? What do you think? Oh, sorry. You have the energy. Do you want to find the wavelength or the frequency?
Wavelength.
Try the other one.
Frequency.
Yes.
The one that I said the first time.
And what formula do you want to use for that?
We could use the energy one.
Yeah. How's that go?
Yeah. We just F equals E over H.
Right.
Oh, I guess we're.
No, that's good. That's what I wanted. So if E equals H times F, F is E over H. Cool. I'm down with that. Our E is 1.6 times 10 to the minus 15 joules. Our H is 7 times 10 to the minus 34 joule seconds. Punch them up.
Two 0.3 times 10 to the 18 joules.
I like it. Wait, but not joules. Christopher, joules cancel out.
Is that seconds then?
False.
Or am I on? Okay, I am on crack.
Wait. So why is seconds not correct, Christopher?
I have no idea.
Does anyone have any idea? See, y'all, you don't pay no respect to the denominator. That's your problem. You kids today have no respect for denominators. If seconds is in the denominator, that does not mean your units are seconds.
So it would be
That's right.
1 over seconds, which equals hertz. 1
That's
hertz.
my point. Seconds is not the same as per seconds. Per seconds is cycles per second or hertz. Okay, what's the formula for wavelength?
Wavelength equals C over F.
Very good. I like your algebra skills. The speed of light is 3 times 10 to the 8 meters per second. The frequency is 2.3 times 10 to the 18 per seconds. Notice that I constantly flip back and forth between hertz and per seconds. I can do that because I understand they're the same thing. What's that give me?
Um, 1 times 10 to the negative 10th, or 1.3, I guess, for using 2 sig figs. 1.3 times 10 to the negative 10th.
What are my units?
They would be
Meters.
Yeah, meters.
Okay, a challenge question. How many nanometers is that? What's the conversion from meters to nanometers?
1 times 10 to the negative 9th meters in.
So do it.
Would it be? Oh, hold on. I think I did that wrong. Oh, wait, no, it's just 0.13.
Yeah.
That's what I got.
That's also known as 1.3 angstroms, which is an old-fashioned spectroscopy unit that I'll teach you about. But let's box 0.13 nanometers. Okay. Another one bites the dust. We only have one problem left. We are flying. Flying on the wings of an eagle. Wyatt, are you still copying or are you good?
I'm good now.
Okay, I'm erasing.
What's the last problem? 57?
Huh?
The last problem is number 57, right?
Yeah. Do you need a second, Christopher? Oh, okay. You're good. Wyatt, since you're already on the horn here, can you just read 57 since I don't have too many real humans to talk to?
Yeah. So it's how many photons? Suppose that all the energy from a 100-watt light bulb came in the form of photons with wavelength 600 nanometers. No, in reality, light bulbs distribute energy over many wavelengths. See exercise 51. And then A is calculate the energy of a single photon with wavelength 600 nanometers.
Let's pause there for a second, Wyatt.
Okay.
This problem is like, if you ever go to Home Depot and you go to the lighting section, they have like party light bulbs. This is a problem about a party light bulb. 600 nanometers is the color orange. So here's your light bulb. They tell us that the light bulb has a power or a luminosity of 100 watts, but that all of the photons have the exact same color or wavelength, and that color is 600 nanometers. That corresponds to pure orange light. And in part A, they want to know what is the energy of a single photon leaving the bulb. What formula would I want to use for that, Wyatt?
All right, so we're finding the energy. We can use since we have the wavelength and H, we can use the E equals H times F.
Well, what would be the frequency for that?
600 nanometers.
That's not.
No, that's the wave. Yeah, that's a
wavelength.
Well, what I'm not sure what our frequency would be.
Well, do you know the speed of light?
3 point something times.
So if you know the speed of light and you know the wavelength, Devin, I've got a better idea. Earlier, you guys solved for frequency, and you told me that frequency was C divided by wavelength, right? What if I then plug that into this formula here, and I come up with a third formula, which is real slick. The third formula is also the energy of a photon, but now it's in terms of wavelength. I love that formula. I think it's a good counterpart to number 1 and number 2. So let's proceed from there. First of all, is nanometers an MKS unit?
No.
Caroline. No, it's not. Not really. Meters are MKS. Caroline, your job is to convert 600 nanometers to meters using dimensional analysis. Can you swing that?
So nanometers goes on the bottom, or like
Yeah, so 600 nanometers. Yep, and what goes on top?
meters.
Okay, what's
Wait,
my...
what do I?
Look at your previous problem. We had it right there in the previous problem.
1 on the top, and then 9 times 10 to the negative 9.
No.
Oh wait, that I did that backwards.
Yeah.
1 on the bottom, and then 9 times 10 to the negative 9 on the top.
Did I write that? It's 1 times 10 to the minus 9. I sure hope I didn't write that as 9 last time. Okay, do you know what 600 times 1 is?
600.
Well, then this must be 600 times 10 to the minus 9 meters. After all, that's what a nano is. A nano is 10 to the minus 9. Let's plug this into our energy formula. The energy is Planck's constant, 7 times 10 to the minus 34 joule seconds, times the speed of light, 3 times 10 to the 8 meters per second, divided by 600 nanometers. Punch them up. It's 10 seconds.
.5 times 10 to the negative 19.
Units?
Joules.
Excellent, Christopher. Box that. That's part A. Wyatt, read me part B when you're ready for it.
Yeah, let me just write down the answer real quick.
Yeah.
All right.
Oh.
Part B. How many 600 nanometer photons would have to be emitted each second to account for all the light from this 100-watt light bulb?
In other words, we're looking for the number of photons per second, right?
Yes.
Let's start with our energy flow of 100 watts. 100 watts is equal to 100 joules per second. Now, we could try to think our way through this problem, Wyatt. But you know what a cool alternative to thinking is?
Not thinking?
Yeah, not thinking. And not thinking is dimensional analysis.
I like that.
Yeah. So let's just put in a division bar. The units that you currently have, Wyatt, are joules per second. But the units
Yes.
you would like to have are?
Photons per second.
So how do I do that dimensional analysis wise then?
We're gonna have to turn joules into photons.
So tell me what to write.
Well, we'll have joules on the bottom
Yep.
and photons on the top.
If only, Wyatt, if only we had a conversion between joules and photons,
Wouldn't that be nice?
wouldn't that be cool?
Um,
Where would we find such a thing?
would it be in the previous problem?
Exactly. So talk to me.
So then would it be the 3.5 times 10 to the negative 19th joule? Like that would be one photon.
Yeah,
So you'd
very
up.
smart. That's joules per photon after all, right?
Yeah.
Photon is kind of like a dummy conceptual unit. So tell me what to write, Wyatt.
3.5 times 10 to the negative 19th photons. Right?
No,
No?
it's not 3.5 times 10 to the minus 19 photons. You can't have half of a photon.
Oh, because it's divided by, it's joules per photon. So then,
Keep going.
geez.
You're almost there.
I'm not.
No, you're there.
I know. I'm just trying to think of what we have to do. So, would you just?
This is. Let me help you.
You just said it.
Yeah.
You had it. What? You called it. That was one photon.
Yeah.
One photon.
Oh, okay.
Yeah,
All
you
right.
had it. You had it.
Okay. Yeah. All right. I understand now.
It's 3.5 times 10 to the minus 19 joules. Very good. No, that's still a bang up job. Usually I have to push people longer for them to realize that that's like a secret mini conversion factor.
Yeah.
Okay, punch them up. Tell me what you get. Joules are going to cancel.
.9 times 10 to the 20.
Units. I'm going to call it 3 times 10 to the. It's about.
I'd want to say photons per second.
And that's correct. Wyatt, when you're finished with that part C.
Yep. Based on your answer to part B.
Oh, wait, I'm sorry. Wyatt, before you launch into it, class, I need to at least erase part A, okay? I need to erase up here. Okay. What's part C say, Wyatt?
All right. Based on your answer to part B, explain why we don't notice the particle nature of light in our everyday lives.
Another way to state the question is, why can't we see one photon?
Because it's really hard to differentiate the tiny one photon from all of the other ones that you see all the time. Is there like...
Wait a minute. Would you say a grain of sand is tiny?
Yes.
Compared to a photon? No.
If you hold sand in your hand, can you see an individual grain of sand?
Yeah.
Yeah, I've seen individual grains of sand. So just because there's a lot of them does not mean you can't see a single one. Too many is not a good enough explanation. There's too many stars in the sky, but I can see stars. There's too many people on Earth, but I can see people.
They're too small.
It is true that 600 nanometers is quite small. You would not be able to see a grain of sand if it was 600 nanometers, but here's the problem, Wyatt. We're not talking about sand, something with matter. We're talking about light. It turns out that all orange light has a wavelength of 600 nanometers. If 600 nanometers was too small to see, then you wouldn't see the color orange. So too small can't be the answer either. I need another idea.
Is it because it's not entirely matter, it's a wave?
It is a wave, and it's not entirely matter. And yet, our eyeballs detect light. You see my face not because it glows, although it actually does glow, but save that for later. But mostly it's light from my background blinds that are bouncing off my face and into my little camera here. So the fact that it's a wave, the fact that it's not solid matter cannot be a good enough answer because all light is waves and we detect light, surely.
Could it be the speed that it travels?
I agree. At 3 times 10 to the 8 meters per second, light is surely fast. It's the fastest thing in nature, but there's just one problem with that. All light travels at 3 times 10 to the 8 meters per second. So if light was too fast to see, how would you see any light? Because this light's traveling at 3 times 10 to the 8 meters per second. But you can certainly see that. Geez, we seem to be hitting all the topics here.
I feel like this is a trick question.
It's not a trick question. There is an answer, but you have to think in more abstract terms. I'll give you a little hint.
Is it because, well, if you think about one photon of light, it's going to have a specific wavelength. So
600
maybe we,
nanometers in this case.
yeah, so what if we can see them, but we differentiate them as colors rather than seeing them as a different
I didn't
size?
really get into this today, but color is just wavelength.
Is it too bright?
Too bright? You're piquing my curiosity here, but too bright doesn't sound just right.
Like, so we can't measure, like, so we can see multiple, like, photons, right? But we can't, like, exactly extract one photon because it's too bright for the retina, maybe?
No. If it was too bright for the retina, your retina would get blown out. This is what happens when something is too bright. That's what it's like. That's too bright.
Okay, here's my train of thought right here, is that I've seen a video of people with a high-speed camera
Shining a
capture
photon through the Coca-Cola bottle, right?
Yeah, so we can see a photon of light, right? Or is that little speck that we saw more than one photon? There are so many packed into that one little spot that you can differentiate them. They're too close
Even
together.
that little pulse, that's what an optics professor would call a pulse. That pulse wave contained zillions upon zillions of photons.
Jeez.
Remember, that pulse was still about a couple of millimeters long. It wasn't.
It was a laser.
Yeah, or as a burst of light. Look, let me ask you this. Here's a thought question to drive you towards the answer. Imagine I could make the world's tiniest Home Depot party bulb, a quantum party bulb. And imagine that this bulb could produce exactly 1 600 nanometer photon per second. If it could produce 1 photon per second, what would be the luminosity or the power of that bulb? In other words, what would be the wattage of a tiny quantum bulb that produced 1 600 nanometer photon per second? Can you answer that question? What would be the wattage of a quantum party bulb that produced 1 photon per second?
One? Like,
no,
I don't know the unit.
Not 1 watt. 1 photon per second is not 1 watt. Like 100 watts is 10 to the 20 photons per second.
Yeah.
So, no. This is 1 photon per second, not 1 watt. Oh, I was hoping that someone might understand the difference between power and energy, but I guess I asked too much of you guys. That job was a little too big for you, wasn't it?
I guess so.
Is it because one photon doesn't have enough energy to be seen?
That's exactly the correct answer. You see, if your bulb produced 1 photon per second, its luminosity would be this many joules per second. It would be 3.5 times 10 to the minus 19 watts. Now look, I can see a 120 watt bulb. These little Christmas bulbs up here, they're probably 1 watt. Can I see a half a watt? Probably. Could I see a quarter of a watt? I think the dark adapted human eye can actually see down to like a millionth of a watt. Can you see 10 to the minus 19 watts? F, no, you can't. Because a single photon is too dim. It's too dim to be seen, not too bright. The correct answer is there is not enough energy in a single photon for your eye to detect it. Which is exactly what, I don't know if that was Paul or whoever the troll was who said that, but that was exactly so. So the trick was to think in terms of energy, not number, not size, not speed, but energy. I think that's a nice wrap up to this day's entire lecture. Okay, you've done it. You've wasted another day learning about photons. We're going to continue our journey. Yay, Gianna says. That was actually pretty good speed. 1 hour and 24 minutes was good speed for a homework wrap up. Okay, can I trust you guys to zap that and send it in ASAP? Christopher, do you want a second here? You sure? Okay. All right, I'm going to stop the recording.